Great. So we're completely overwhelmed by the reception of this meetup. We have never thought that so many people could be interested in Munich, in our little village. Yeah, this is amazing. And so I first want to thank the amazing people that made this possible, which is Vangelis Parasidis and the Google Munich team, who gave us this very lovely location and, of course, the great food. As well as Christian Frank, who has not only thought up this meetup, but also done a lot of the organization. And so we're very thankful to both of them for making this possible. Yeah, my name is Sebastian Ullrich. I'm co-founder of the Lean Focused Research Organization. So that's the nonprofit that is driving the development of this tool called Lean. And today I will talk as the very first meetup. Let's start with the basics. And yeah, specifically why Lean is winning at these basics. And I do like this title because immediately brings up some other questions like, well, what is Lean winning at? And perhaps also, what is Lean anyway? So yeah, we'll go through all of these questions in the next, let's say 40 minutes. I think that's about the goal. And after that, yeah, you're free to ask questions while we're in here, and then we'll just go back to the nice food and enjoy it and have some more discussions until we should slowly be leaving the location at around 7:30. Sounds good? Awesome. Okay, then let's talk about Lean. Yeah, so I'm assuming for today, no prior knowledge. I want anyone who's interested in the idea of Lean to enjoy this talk. So let's just start with what's the one sentence description of Lean. It's an open source programming language and proof assistant. So it's open source. You can download it from GitHub for free. Anyone is free to use it. It is a programming language, a functional programming language. You can write actual programs in it, but also it is a proof assistant. So a tool, a computer program that helps you verify proofs, verify formal logical statements. All right. And so that's a very generic description, but what Lean excels at and what makes it very special are two properties that I've listed here. First of all, well, since Lean is a programming language, yeah. Huh. That's funny. I just talked to Vangelis about this problem of Google Meet sometimes hanging. Seems like I have this problem. Why did that work before? All right. Okay, so how do we fix this? That's funny. It's not even. So usually it's we have to share something else, right? I'm sharing a window right now. You are presenting. Stop presenting. Does that work? Okay. We're not completely broken yet. Let's maybe share the entire screen, and then I'm missing my nice notes. So let me quickly grab those slides. Oh, where did they go? I was not prepared for that. I think sharing Chrome tab is usually what works, right? Let's try that. Yeah, because unfortunately I can't use HDMI, or I think we'll run into problems with recording. So yeah, let's figure this out. Okay, that's one slide. That's not the best view of that slide yet. That's better. And if I can now also get my, oh, that won't work. Okay, I'll just work with that. Okay, looks good so far? Okay, yeah. Let's check with the next slide if that will appear. All right. Okay, and so yes, what Lean excels at is two specific properties that I've listed here, which is, well, yes, Lean is a programming language, a general purpose programming language. So in fact, it is implemented in the Lean language. The Lean compiler is implemented in it basically, and all its tooling around it. And what that means and what that enables is that you can extend as a user, extend Lean without like forking the source, but actually, yeah, just by writing Lean programs, you can also extend the Lean system in actually many different ways, which, yeah, some technical jargon there if that tells you something, but we'll also get back to that later. And then on the other hand, there is this thing in the middle of Lean that in the end actually needs to certify your proof, needs to tell you what is a correct Lean proof and what isn't. And this part, of course, is not extensible. You want to trust that. And in fact, we made it as small as possible, which is in fact where the name Lean comes from, because from this Lean, from this small trusted proof checker in the middle. And in fact, you can also use independent proof checkers for that. So these are two foci of Lean, both the extensibility of the outer shell of the language and tooling, as well as the trust in the middle of what we actually want to prove, and then trust in those proofs. Okay, and then one more ingredient of, I think, what makes Lean special, that's a bit more squishy, but people don't only find nice uses for Lean, but they actually love using the system. And we'll get to some more quotes of that as well, but I like this one by Harry Goldstein from the University of Buffalo, who said, it's not just a proof assistant, also the programming language. Yeah, it's not just a tool for the proof assistant. It is just well designed and modern by its own. All right. So yeah, and this is not just a single quote. I should also mention some recognition we received just last year. The Lean system received the ACM SIGPlan Programming Languages Software Award. That's a yearly award for programming language related tools, as well as the original paper that described Lean in 2015 received the Scholem Award. That's a 10-year test of time award. And yeah, as you can see in both of these award descriptions, the broad and tremendous impact that Lean has had on formalized mathematics, on software verification, and also being the de facto choice for AI-based systems is what was recognized here. And so we'll look at exactly these applications today. Okay, but before we get to the applications, if you haven't seen Lean before, I at least want to give you like one visual impression of what using Lean looks like. And yes, so it is also a programming language. And so in fact, how we interact with Lean is a programming editor. This is VS Code. This is the main user interface of Lean. And on the left-hand side, you have something that looks a lot like standard programming code, right? Yes, and you can program with that, but of course, the specialty, without going into all the syntactic details here, is that you can also write down theorems, write down statements that you want to prove. And then, of course, the important part, you can also explain to Lean why that statement is supposed to hold. And then, of course, the even more important part is that Lean will tell you if that claim is correct or if you have made a mistake in your proof. And so it's really, you should think of using Lean as a game that's being played between the human who like does a game move, like a chess move, and then the system telling the human, or the AI, of course, we'll get to that as well, telling the human, yeah, this was a valid move, and that's how the board game looks now. That's the right-hand side. You can see the response of Lean, or it can be that Lean will tell you this is not a valid move, and here's why. And then you move and move until it's checkmate, until you have actually proved your goal, gotten to the end of your proof. And yeah, this is one other aspect that people just like using Lean for and actually find addictive. Many people have used that word to us. And then, yeah, even professors of mathematics like Kevin Bussard here just says this is his favorite computer game, using Lean. All right. Okay, so let's talk about applications today. And we'll start with mathematics. That was the first big application of Lean. And then talk about software verification as well. And then, yes, we'll get, of course, to one of the hot topics currently, what Lean has to do with AI and what AI has to do with Lean. All right. Okay, so it's not really possible to talk about mathematics in Lean without mentioning MathLib, the mathematical library of Lean. That's, yes, also open source on GitHub. You can check it out there. And what makes this special, since it is open source and since it is written in Lean, is that actually many people can collaborate on this project. And in the end, it's not like doing mathematics in text that you have to trust your co-authors to not make a mistake, because Lean will be the co-author that catches such mistakes. So in the end, we have 750 people already having contributed to this library, pouring it to over 2 million lines of code. And in the end, they can collaborate in this manner because they only have to trust Lean being in the middle, telling them that their proofs actually go well together, that they are all consistent. And so why would mathematicians build a library like this? Okay, they just find it fun. That's definitely one good reason for it, especially in the start. But yeah, like Heather McGrath from Fordham University here, they expressed that they are also doing this because they think this is the future of mathematics. And even if it's just maybe a bit boring at the beginning, just writing libraries, so MathLib is already far beyond the boring parts. They are still doing that. They are putting in that work because they also want future mathematicians using Lean to build on top of that and create exciting projects in the future. And so one example for this project, I want to talk through that, happened in 2020. So that was one of the first big projects being done in Lean. And how did we get to that? Why would anyone do a big project in Lean if we've done mathematics on paper for the last 2000 years and that worked well as well, right? Well, this was actually a project being initiated by the Fields medalist Peter Scholze. So Fields Medal, one of the highest honors in mathematics. Peter Scholze is probably the most well-known German mathematician. And he had a proof in 2019 that he was obsessed with the correctness of this theorem. Like, he has written down the proof. He can read it back. But even he, as the author, was not completely sure that there were no small mistakes somewhere lurking in that proof that would completely invalidate the entire statement. Yeah, and so he'd heard about Lean, and so he posited a challenge. Dear Lean people, or in fact, dear formal methods people, can someone verify this proof for me and tell me that it is, in fact, 100% correct? And yeah, amazingly at that time, people came actually together, a small team of Lean formalizers under Johann Kommelin, and they completed the critical proof within a year, the one that Scholze was not completely sure about, and then the full challenge with all the further theorems within one more year. And I mean, they couldn't do this because they were smarter than Peter Schulze. They specifically said they did not understand the full proof. No one of them did. But yeah, the crazy thing is they didn't have to, because the only thing they had to understand and had to tell Lean is how to get from one state in the proof, for example, from one helper theorem to the next one. And then Lean is the system that can hold all of that in memory and say, yes, all these parts come together as a whole to actually prove the entire statement. And yeah, I also just love this quote. Peter Scholz, as a mathematician, is really using computer science metaphors here, saying the proof did not fit in his RAM anymore. But yeah, using Lean, how this team did it for him, you really have an assistant, yes, a proof assistant that lets you navigate through what he calls a thick jungle of a proof. Right, and so that really was only the beginning. We've seen many very ambitious projects being done in Lean since then. Yeah, I won't go through all of these today. Also, I'm a computer scientist. I can, yeah, for half of them, I can probably not even tell you the statement. Let me just point out one more name on here, which is we have Terence Tao, another Fields medalist, maybe the most well-known mathematician of our time, also come in and actually learn Lean and do his own projects in Lean. And as you can see, he wasn't satisfied with just one project. When that was done, he started another one and then another one. So he is also addicted to Lean. And actually, if you're interested in that, you should absolutely check out his Mastodon account. Just like a search for Terry Tao Mastodon. He talks a lot about Lean, about formalized mathematics, and there's also applications of AI for that on there. It's really interesting to read through that. Okay. Yeah, but for today, I instead want to talk about the other topics as well. I assume we don't have, do we have mathematicians in this room? Let me just check, even now that I'm finished. Yeah, okay, great, great. Yeah, then we have a nice crowd. I'm really happy with that. Yeah, but for now, let's switch to computer science as well. Let's talk about that as well. And yeah, so why do we want to verify a software? Well, of course, because software has bugs. I think anyone who's ever written software is very well aware of that. And yes, Lean is a programming language. So it's a language where we can write bugs in. But the very interesting part is that, of course, Lean is also a proof assistant. It is both in one system. And so you can immediately, after you've written a program in the same system, in the same file, you can also reason about it, meaning you can prove that your code has exactly the properties that you expect. And why this is so important, already Edgar Dijkstra has succinctly expressed that in his time, is that, well, we all do unit testing, right? But by unit testing or manual testing, we can find bugs. But we can never show that no more bugs are left in our code, because usually we have like an infinite input set of inputs. We can't just test all of them. Users will always come up with new inputs, unfortunately. Yes, but with formal verification, you can just think, we can say, for all inputs, something holds. That's a logical statement. That's something you can express in Lean and prove in Lean, but you can't do with testing. Okay, and I'll talk about software verification in more detail, but I also want to emphasize here that Lean is not only for verified program. Remember that Lean is actually written in itself. So it is a capable general purpose programming language. Also remember the quote by Harry Goldstein. And so it is not only a formal language, but it's something you can actually run on your machine. You can compile into native executables, put on your server, and so on. And of course, for that, we are also providing a rich standard library that goes beyond what you might be interested in when it comes just to formal verification. So yes, we have I/O, we have actually asynchronous I/O as well, plus networking. We have a datetime library because, yeah, when we program, sometimes we have to talk about dates and time as well, even if it's a fuzzy project, fuzzy concept, and actually quite interesting also to verify. We have concurrency primitives. We have collections like sets, hash maps, and these are in fact verified. So even if you just want to write a program in Lean and not worry about verification of your program, you might just sleep better if you know that the actual hash map you're using has been verified to always return the correct result, right? And iterators and so on and so forth. Really, yeah. If you're interested in the standard library, look at the code, look at the talks my colleagues have given on the standard library. There's a lot of great work in there. Okay, but for today, let's stay with software verification, because that's, of course, something that not many people are doing yet. And so one example that I want to talk about in more detail is a project called SAMCert that was developed at Amazon Web Services. It is open source again. You can check it out on their GitHub. You can look through their proofs, look through their statements. And so what's it about? It's about verified differential privacy primitives. Even if you haven't heard about differential privacy yet, I think could be immediately clear why privacy is something that is very important to AWS, and where they also want to show their customers that they have implemented this correctly. The differential part is also good to point out, because yeah, this is actually about differential in the mathematical sense. And so in fact, this computer science project is based on Mathlib. It's using a lot of the probabilistic methods and so on defined in Mathlib. So this is actually a very nice project that combines the strengths of Lean into one project. All right. So yes, they verified it in the end. They were able to prove that there were no bugs in their implementation. But then the more interesting part, I think even more interesting, is that they made it twice as fast as the unverified implementation that they were basing their implementation on. So how does that work? I mean, Lean is a fast language. We like to make it faster and faster, but it's not just twice as fast as some C++ program or something else you've written. It's not that great. Yeah, but what happened instead is that since you have this guarantee of the implementation being correct, corresponding to your proofs, you can actually apply optimizations that are, yeah, maybe just very complex, where in other languages you wouldn't be sure, okay, is it worth the potential bugs that this optimization introduces, the wins in runtime? And yes, if you use verified software like this project, then this is not a problem. You can prove that the optimized implementation has no bugs either. So you only have to think about, is this optimization worth extending my proofs for? Right. So yeah, I think that's a really nice example, just that it's not just about being correct, but actually what you can do with that knowledge. It's similar to for the mathematicians. It's not about just making sure that the theorem they maybe already knew about is correct, but also that they can work together in new ways and in much larger numbers than when they just have to trust each other. Okay, and so of course it's not just this single project. There are many more open source projects that you can check out. I listed 3 here. I actually, for this slide, I didn't go far. I just looked at the last 2 weeks of announcement around verified software in Lean. And so there was an announcement from the Ethereum Foundation for their verification framework around zero knowledge proofs. So that's also, again, something that nicely connects between computer science and some mathematics. We had another company come in and write a nice blog post on optimizing compilers for cryptographic primitives. So you're doing some very special case optimizations in your compiler for cryptography. And then, of course, you want to be double sure that this was actually a correct optimization. And they proved that for all the inputs to their compiler. And last one from a university, found very nicely FLOPS project, which is a formalization verification of an upcoming IEEE standard for floating points. And yeah, floating points are notoriously hard to get right. It's really good to have a proven, consistent standard and formalization of that, right? Okay, and so if that's only the last 2 weeks, then it might not surprise you that computer scientists are also coming together like the mathematicians and thinking about how can we provide the best foundations for future projects. And yes, so now we also have, in correspondence to MathLib, we have ACSLib, which is a focused effort on formalizing computer science in Lean. Yeah, and this is being supported by both industry, AWS, Google DeepMind, of course. It's nice for today's host to mention the University of Southern Denmark and Stanford University. Okay, yeah, so many big companies are being interested and are investing into this software verification topic in Lean. And then even one level lower, what's the tools that you actually use to verify such programs? Of course, Lean provides like the base logic. You could just work in that. But yeah, we have seen people work on abstractions on top of that. So for example, from Singapore University, we have Velvet, which is a program verifier for imperative programs that you embed into Lean. And so that directly uses the extensibility of Lean to say, oh, I could just embed a different language that looks nothing like Lean into Lean. And then I can still do all the formal reasoning, do all the proofs that I could do about Lean programs. Yeah, we have other languages. There is a Rust verifier, so you can take an existing Rust program, have it translated into Lean programs, and then do proofs about those Lean programs. Yeah, that's also being and was developed at INRIA, France, at Microsoft Research, and at Google as well now. From Amazon, we have Strata, which is a unified platform for formalizing languages. So now you can express arbitrary languages in Lean. And yeah, last but not least, we are also working on the foundational level. Yeah, that's just for Lean programs that you have actually written in Lean that are just functional monadic programs. How can we make it easier to prove those correct? And so for that, we have a framework now called MVCgen. Right. And with that, I already want to get to the last application area where Lean is being applied currently. So, yeah, AI. The last application that I want to present today, I should probably say. And let me start there with a show of hands, because I'm interested in that. So who in this room has written code with like non-trivial AI assistants before. Okay, that's well over half of all people. That's almost basically everyone. Very interesting. I mean, yeah, I'm definitely counting into that as well. And so out of these people, how many have seen the AI introduce true, not and probably maybe even subtle bugs into your code that it generated? Yes, that's basically the same number of people, I think. And yeah, we all know this is happening, but it keeps happening to us. And we also know there's no real, right now we know of no solution to tell the LLM to just not make a mistake, right? We should. Yeah, and maybe if you add please as well, that gives you another 5%. But yeah, I don't think you get to 100. Yeah, so, but we can, of course, combine what we've already seen about Lean, about program verification, with this approach and actually verify the output of AI, of our programs in Lean. And of course, this works equally well for mathematics. If an AI finds a proof, well, will you just trust the AI? Probably not, right? Mathematical proofs are maybe, I mean, if they get to 200 pages, they are probably even more subtle than correct programs. And yeah, just like Peter Scholze was worried, even just from his human output, if there's any small mistake somewhere in that proof, you can probably throw away the whole thing. And so, yeah, the correct combination in our minds is to take the AI output and have it, or rather have the AI create a machine checkable proof, a Lean proof that you can then run through the system and actually get back basically a certificate, a check mark that tells you, yes, in fact, this AI output was not hallucinated. Right. And so I want to show a bit of history, how all of this started, because, yeah, again, this is very nice for being our location today. The first, I think, major result we had with AI, and this was about AI plus mathematics in Lean, was by Google DeepMind in, what's the year again? Let me check. Yes, 2024. Just wanted to make very sure I'm not saying the wrong number here. Yes, in 2024, they created an AI mathematicians, basically immediately got in the New York Times, move over mathematicians, here comes Alpha Proof, that's their software. Yes, and they were very successful with that. And the crazy thing is, no one at that time in 2024 expected that we were so close to AI software actually competing in mathematical competitions, because that's exactly what they did with Alpha Proof. It was completely out of the blue, this result. And yeah, so they did it in Lean. Why did they do it in Lean? Fortunately, we don't even have to guess. The vice president of research was very explicit about that in a comment. Yes, it is the extensibility and, yeah, of course, the verification capabilities of Lean that enables them to create the software. Yeah, the verification part immediately makes sense, right? That's exactly what we were talking about, how we can make sure the AI actually creates a proof. But let's quickly think about why extensibility is also important for such applications. Because, well, what's basically the most important thing for machine learning? It's creating and consuming data as much as possible, right? And yeah, when you have a system like Lean, where you maybe already have quite a few proofs having been done in that and that you consume, it's still crucial to consume it in exactly the right manner to tell the system, the AI system, as much as possible about the details of the proofs. And so this might not be necessary to just have it look at the text of someone that someone wrote in Lean. But instead, inevitably, you'll want to create tooling around your system that can interact with Lean, that can find out more about a proof or what's the intermediate states that are not actually in the text. And then, of course, for the AI to actually find proofs, you'll want to send it like one step to Lean, get back the result, yes or no, what's the next board state, just like we've quickly seen for humans. But yeah, that's special case for AI systems as an API. And for this, yeah, the great thing about Lean is you can just use exactly the same API that we are using to build Lean, to build the Lean tool. You can use exactly the same for your AI to talk to the system and construct proofs and consume data and so on. Okay, so what exactly did they do? Yeah, they had their system participate in the International Math Olympiad. That's like a competition for the brightest high schoolers. And yeah, their system consumed the question, the problem statement in English, and then it created a Lean proof from that. And of course, it had Lean check the proof that it is actually correct. And yeah, with that approach, with of course a lot of things happening in between, that you can also read up on at their blog. They got within 1 point of what for a human participant would have been a gold medal. So that, yeah, that was the part that everyone else was completely surprised by. In 2024, we did not see this happening. We thought, like many mathematicians at that time thought, that was still years away, such a result. And then, of course, the exponential development of AI happened just here as well. So last year at the IMO 2025, we already had many different companies declare their results and also claim a gold medal as well. So what's next after the IMO? Yeah, well, let's go to the undergrad level. There's a Putnam competition for that, and yeah, the exponential growth continues. Basically, by the end of last year, this was already being completely solved. The 700 problems of the entire history of this Putnam University level competition. An AI system based on Lean for verification was already solving almost all of them. And yeah, we really started like at the very left. We have GPT-4o, so not a Lean specialized system, maybe solving one proof, one statement in July of 2024. And yeah, even on the right side, we still have GPT-5 at the end of last year solving 28 problems. So yeah, it's not just raw AI that we can throw at these problems. You really have to think about how can you create something that interacts well with Lean to create these spectacular results. So yeah, all of these systems on the blue curve are backed by Lean for their verification. Right. So what's next in AI? In AI plus mathematics, what's even left? Well, if we've basically gone through the competitions, let's look at open problems, right? And that's exactly what you can basically watch the AI companies do that live on social media. And so, for example, at the end of last year, they were all going through the open problems that this famous mathematician, Paul Erdős, has written down without solutions at his time. And yeah, they were going through that, finding new solutions, finding Lean solutions, different solutions to existing problems, finding solutions in literature that nobody knew about. and collecting all of this. So yeah, this is just to say, this is an extremely dynamic space. And we're also very happy to see not only the big AI players play in this, but really startups forming around this idea of how can we make mathematics even faster? How can we find proofs in a more efficient way using AI? And yeah, while the focus of what I've just shown so far is on mathematics, I don't think it's hard to see that anything they're applying to mathematics and that works well should similarly apply to program verification in the future, and so help with that and make us more productive when it comes to verifying programs as well. Yeah, so we're incredibly happy to just see this ecosystem come around Lean. And really with that, I should slowly get to the end, that we also have some more time to enjoy the nice food and enjoy each other's company. But before we get to that, hopefully I've motivated Lean to you now. So maybe now is also a good time to answer the question, well, who are we anyway? And what's happening in Munich around Lean? Right, so I mentioned we're from the Lean Focused Research Organization. So what exactly does that mean? Yeah, so we are a non-profit. I think I mentioned that before. So we don't sell Lean, we don't sell Lean consulting. We're simply creating this open source project. And yeah, there is, of course, always something to improve when it comes to such complex software. And so what we're focusing is scalability. How can Lean cope with even more complex, even longer proof? Well, I mean, we already have these 2 million lines of code in Mathlib. Just compiling through that, there's always something that can be done to make that faster. On the other side, we also want to make Lean stronger, of course. That's the proof automation part. So the basic steps that you can use in Lean. And maybe you're thinking, well, won't we have AI just for that? It can just write a Lean proof for us. It doesn't have to be, Lean itself does not have to be intelligent anymore. But I think the very opposite is the case. The more clever, the more complex the basic steps are that you can express in Lean, the easier the AI can make use of that and find even more complex proofs. And then, of course, yes, usability and documentation. Yeah, we want Lean to be usable as easily as possible and are continuously working on that. Right, so this foundation, a focused research organization, exists since August 2023. And we have now 21 people working on Lean and its surrounding tooling. And this is all being supported, I should certainly mention that, by philanthropic sponsors that, yeah, are just as interested in the goals and visions of Lean as we are. Yes, so what's the future of Lean? This focused research organization concept is a time-limited project part where you really push a project for a set amount of years. And so eventually, by establishing Lean in all of these applications that we've seen today, we want to turn it into a permanent Lean foundation. Yeah, and yeah, we've been very busy ever since Leonardo de Mura, the creator of Lean, and I created this Lean focused research organization. And we are basically running this as a startup. We are neither in academia nor in industry, but really somewhere in between. Okay, yeah, just to put some faces to this work, this is our amazing team that is making all of this possible. And yeah, especially today, I also want to emphasize that a great number of these 21 people. That's, I counted that. Can someone count for me again? That's 11. Great. Yes, yes. It's just over half of our team is located in Europe. I'm happy with, quite happy with that as well. Germany, yeah, I really have to say, 8 of these 11 people, it's a powerhouse of lean development. And yes, then finally you have, we have a little office in Munich of our 3 people. That's, yeah, if you want to talk to them today, that's me in the middle, that's Mark over there, as well as Henrik. And I should also announce Joachim is joining us today from the lovely Freiburg. Right. So yeah, let me just summarize. What we've seen today is that, yes, Lean is a programming language and proof assistant. That is the core of it. But yeah, we make no compromises on either part. It's not just some language that you can prove things in. No, it is a language by itself with a standard library, with efficient execution, and so on. Yeah, the other core ingredient of Lean is its extensibility, and really Lean being written in itself makes sure that all of this API that you could possibly want and need to talk to Lean is in fact in there. Yeah, we have talked a lot about machine checkable proofs, why we want that, and why we might want that even more in the age of AI. And yeah, we're supporting all of these applications with a new word coming in with each release as more and more is happening. So yeah, really ultimately what we want to make sure is that verified software, that's something that people just do, especially when AI is involved, and not something that is reserved for very special projects. Yeah, and with that, there's one very important thing that I just wanted to make sure that I'm mentioning again, just as a double checking slide. So yes, thank you again to Google Munich for hosting us today, for Vangelis Parasides for the organization on their part, but to the entire Google Munich team as well as Christian Frank for the co-organization of this meetup. And thank you as well for joining us today in such amazing numbers. This is incredible. Thank you. Great. So we're basically on time. I can maybe make one suggestion if you're interested in that. Or yeah, if you haven't already seen Lean, then feel free to just get some food. I can also give a quick demo of just getting a bit more of the feel of using Lean. Would that be something that people would be interested in? Okay, great. Yeah, that was a quick idea we had today from Mark. Thank you for the idea. And yeah, I thought then I can take a few more minutes of the second part to make sure we have this covered as well. Now I just have to make sure that we're actually sharing this correctly. I think I will stop recording. Then we can maybe get first to questions if there are any, and then I will do the demo. All right.